Previous figures had shown that TEB4 may potentially be an integral ER protein with the N-terminus projecting into the cytosol and the C-terminus protected within the ER lumen. Earlier in Figure 3, the authors had shown this is in fact the orientation within pancreatic microsomes, and here they attempt to show that in vivo this is the orientation within mammalian cells. Here they used hamster cells expressing TEB4 from a plasmid, which were then metabolically labeled with radioactive sulfur. The cells were permeabilized, treated with proteinase K, and the internal membranes lysed and spun down. The pellet was resuspended and immunoprecipitated with the N-terminal and the C-terminal antibodies directed towards TEB4. In both cases, without proteinase K treatment, we see that the antibodies pull down a significant amount of TEB4. However, for the N-terminal antibody, when proteinase K is added, we don't see any significant fragments pulled down by the antibody. When the C-terminal antibody is used with low concentrations of proteinase K, we see a small cleavage product at about 34 kilodaltons, which the authors claim is TEB4. A larger amount of proteinase K diminishes the intensity of the band, and treatment with NP40, which lyses internal membranes, makes the band disappear completely, indicating that this band can in fact be cleaved by the proteinase K and is not simply an artifact of the assay. From these results, it appears to support the author's hypothesis that the N-terminus is in fact projecting into the cytosol where it is accessible to proteinase K degradation, but that the C-terminal portion is protected within some subcellular compartment from proteinase K degradation. However, this assay does not prove which subcellular compartment this is. Figure 4 is used to prove which compartment this is and prove it is in fact the ER. Here the authors are trying to show exactly which subcellular compartment TEB4 localizes to. To do this, they've used two sets of HeLa cells. One's transfected with wild-type TEB4, the other transfected with TEB4C9A, which is simply a ring finger disruption of TEB4. These TEB4s are conjugated to a MIC tag, which is easily detected by a primary antibody. A second antibody is then used to detect the primary antibody, and the secondary antibody gives immunofluorescence, shown here in red. So what we're observing in panels A and D is the subcellular localization of TEB4 with which the authors claim appears to be ER associated. To prove this, they use calnexin, shown here in green using the same immunofluorescence strategy. Calnexin is an integral ER protein, and so what the authors do is overlay the two images, showing that when red is overlaid with green, we get an orange image showing that TEB4 associates to the same place that calnexin does, or the ER. From this data, the authors conclude that TEB4 is an integral ER protein with the orientation they have determined in Figure 3D. In Figure 7a, the authors use an in vitro assay to attempt to show that the TEB4 ring finger domain is necessary and sufficient for ubiquitin ligation, and that this ligase activity requires the availability of a K48 residue in the ubiquitin substrate. What we see here is the various reaction components separated by SDS page and stained with Coomassie. Lanes 1 and 2 simply serve as controls to show where HSUBC7, the E2 protein, and the GST TEB4 ring finger fusion migrate within the SDS page. Lane 3 shows that when E1 and MYC ubiquitin are added, E1 is able to activate the ubiquitin and transfer it onto HSUBC7, resulting in a partial fragment of HSUBC7 migrating at a higher molecular weight due to the addition of the ubiquitin. In lane 4, we have the exact same reaction, except with the addition of the TEB4 ring domain. What this should allow, if it is necessary and sufficient for ligation, is the formation of a ubiquitin dimer, which the authors claim shows up here at approximately 20 kilodaltons. Given the fact that E1, the GST TEB4 fusion, the ubiquitinated and unubiquitinated HSUBC7, and the ubiquitin are migrating at approximately the same positions, This appears to be a reasonable conclusion. In lane 5, we have the same reaction, but with the K48R mutant of ubiquitin added instead of the wild-type ubiquitin. If the authors are correct, this should result in a loss of the ubiquitin dimer as shown here. Given that all the other components of the reaction are migrating at the same position, this appears to support the author's conclusion that the K48 residue is required for the ligase activity of the TEB4 ring domain. Figure 7c shows an in vitro activity assay where fluorescently labeled ubiquitin, indicated by the asterisk, is attached to UBC7, the E2 partner for TEB4. What we see here is an assay where the authors have added various ring fingers as well as a cold, unlabeled version of ubiquitin, which is unable to be activated and therefore must act as the substrate to which the fluorescently labeled ubiquitin is added if there is ligation activity. The leftmost reaction shows a negative control with no ring domain, showing the majority of the fluorescently labeled ubiquitin resides with UBC7. The rightmost lane shows the positive control, where HRD1 ring, a previously proven E3 ligase, is used and is able to catalyze the transfer of the fluorescently labeled ubiquitin to the cold substrate. TEB4 wild type is also added in a separate reaction, which also shows transfer of the fluorescently labeled ubiquitin to the cold substrate, confirming the previous result that the TEB4 ring domain is necessary and sufficient for ligation activity. The authors then go on to assay if this ring finger structure is critical, and in doing so they create the C9a mutant, which is previously shown to disrupt other ring finger activity. Here they show that the C9a mutant gives transfer that is approximately equal to that observed in the negative control, leaving the majority of the fluorescently labeled ubiquitin attached to UBC7.